Yeah, g'day, Mark here, and welcome back to my channel. Now, a couple of weeks ago, I did a video on my overly complex attempt to bring the overly complex drive system of my lathe under Linux CNC control. And of course, I failed. So this week, I'm going to try and simplify things. Now, before we look at my next attempt at control software, what was I trying to do and why did it fail? So what I was trying to do was ideally have the continuously variable transmission hold the motor at approximately 50 Hertz where possible. So try and keep the motor at its sweet spot for best torque, best cooling, best everything. There will be some spindle speeds where I'll end up on the lowest gear ratio and therefore drop out below that and therefore need lower frequencies. And the same, there's probably some frequencies above as well. But for most of the time, I was kind of hoping to keep the motor at about 50 Hertz. The problem I've got is there's no good feedback of motor speed at this stage. So there's really two issues. One, I've got this massive change in inertia in the system between lowest low gears and highest high gears. If I'm going to closed loop control the motor with the VFD, I'm going to need variable PID gain staging to avoid either oscillations at one end or extremely slow performance at the other. To work out which gains I need to know my ratio. How was I calculating ratio? Well, speed out is known, but speed in, the only thing I had was commanded speed, which, okay, commanded speed, output speed gives you ratio. However, if you think of how this works, when Linux CNC commands a speed, this value instantaneously changes. So if you want max speed, it'll transition from 0 to 10 volts nearly instantly. But the whole system's got a lot of mechanical inertia and has to accelerate up to speed. And because the system was calculating that ratio 1,000 times a second, the first time it calculates it, it's seeing 0 speed out, maximum speed in, and sees a nearly infinite gear ratio. As the system accelerates, that gear ratio will reduce, and eventually at a steady state, you'll be able to actually read a reasonable number. So what I was trying to do with software was put a gate on that calculation. Do not calculate gear ratio unless you're at steady state. But I ended up with a system basically chasing its tail. I only ever got it working either very slowly. It would change a gearbox ratio, wait for a while, calculate the new ratio, change the speed to match, wait a while, check the new ratio, and therefore the speed would be too high, wait a bit, correct, go too low, wait a bit, go a bit higher, wait a bit. And I had this very slow control optimization or speed optimization. I got a huge amount of feedback on the last video, and I really appreciate all of your inputs. So I've gone through them all, read them all, and tried to summarize them. If you look in the video description of that last video, you can see a summary of all of the different recommendations of how I could go about improving the system, and also my quick idea of what I'd like to do next. To summarize the advice I've got, what I'm effectively trying to do is control two different feedback loops, one to the VFD and a slower one to the continuous variable transmission, but I've really only got one equation, and therefore I could only do one or the other and not both simultaneously. If doing a constant surface speed facing cut, when the CVT bumps, because it's driven by a constant speed motor, it changes ratio at a constant rate. And that rate is often too fast for the change in surface speed that you actually want while cutting. So ideally, while this is maybe increasing its ratio, you would want the faster acting VFD to compensate by reducing this frequency at the motor so that the actual spindle speed increases smoothly across the cut. I couldn't get there. Now, most of the advice I received revolved around adding feedback. Put an encoder on the motor, encoders on both sides of the CVT, adding feedback to measure the lever arms here to know where my sheaths of these pulleys are being located. Most of the advice centered around that. And it's good advice, and will probably be necessary in my third attempt to get this working. But being a bit pig-headed, there's one more attempt I'd like to make before I add any more feedback. So let's go back to basics here. I've got a user manual for this machine. So let's try and work out how Schaublin originally did the gear changing. Maybe there's some clues in there. So here we can see that the spindle under the original controller from the early 1980s had two different control modes. You could command one of 38 discrete spindle speeds between 48 and 3000 RPM, or you could command one of 42 surface speeds between 8 and 900 meters a minute. So while the machine is in motion, the RPM cannot be changed. So those 36 different speeds divided by two different gearbox speeds and two different motor speeds means they created 9 individual gear ratios off the CVT. Now, I never had this machine working under its original control. I don't know if it's those selectable surface speeds means it could do a constant surface speed cut across the face, or whether that just meant whatever surface speed was right for the start of the cut would be set and then it would be continuous. But let's just assume it couldn't do a constant surface speed cut, and all it did was just divide up this whole system into 36 individual gear ratios. Let's try and duplicate that and see how it works. Not sure if I've ever shown this before. This here is my knife sharpening jig. I know you can buy these things for hundreds and hundreds of euros, but I just whipped this up out of a couple of aluminium profiles. Piece of linear bearing. Had to cut the alignment bits off this bracket so that I could rotate it. The height of this adjusts the angle. I think it's at 20 degrees if I remember rightly. The linear rod goes into a spherical bearing to give a bit of motion. I took a piece of water pipe, turned both ends to fit linear bearings, and then just epoxied 4 different grits of stone onto the outside. As you can see, they're starting to look pretty worn by now. Should probably get some new ones. I realized after I'd made it that this is probably not the most convenient mounting method. I've since seen that the better versions of this mount the knife on some sort of a system which you can flip it over, so you can do both sides at once. I have to do one side at a time. But oh well. I had written on there what the different grits were. Let's see if I can still see them. Well, this was the finest, so I'm guessing that this is the coarsest. This is one of my kids' knives, so my guess it hasn't been sharpened in like ever. Unfortunately, these linear bearings work a bit too well, and it always wants to fall down. Right, with that done, the last task is just to go through each of the knives, hone the edges a bit. I guess if this was a knife making website now, I'd go through and like do a samurai sword slash or something, or cut some paper, but you just have to trust me, these are now sharp enough to cut up a chicken. Right, I need to populate my lookup table with all of the different speed steps. Right, I've now got it set up using those two lookup tables for the low gear box speed and the high speed. There's about 35 or so steps of different speeds between lowest and highest, and the control component just open loop commands the CVT and the VFD into their commanded speed positions. The very first startup after starting the machine, the VFD starts to 10 Hertz, and then the variable transmission bumps right through for 6 seconds to end up on its slower speed stop. So we've got a known starting position. I've divided the CVT into 12 bumps of 0.42 of a second per bump, and then it's all just open loop. However, I did put a wee bit more in there. I've got a motor at speed pin which outputs from the VFD. So I'm using that to inhibit the system calculating the gear ratio. Anytime that inhibit opens, so anytime we're at constant steady state speed for more than a second, I let the software calculate the gear reduction ratio and compare it to what it thinks it's at from the lookup table. And if there's a significant discrepancy, I don't try and do a closed loop, regulate back to the correct position. I just tell it to add or subtract time to the next CVT bump to try and correct the error. Let's see how it works. So starting at 500 RPM, we've got that startup CVT bump mechanism. And our speed is slightly high, 520. Okay, let's go up to 1000. Yep, slightly high, but very good. 2000. Maybe 800. 2,500. Whoops. It's a bit slow. Oops, that was not a speed. Let's try that again. Well, that's really not looking too bad at all. Most of the speeds set were easily within 10% of their target, mostly slightly below, a couple were slightly above, but you know, how important is it really to have speeds within a couple of percent? Let's have a look at the back gear. I'm going to need to develop the software further to take advantage of the VFD's electrical braking to more rapidly change down from high speeds to low speeds. I don't know if I'd ever have a use for 20 RPM, but hey, the system can do it, so why not? Can lower range, it seems like the speeds are quite consistently about 10 to 15% too slow, so I might need to tweak my lookup table a bit, but it's certainly working. Let's do a switch back to high gear, just to make sure that switching is normal. Okay, so if that's all working reasonably well, let's now try a facing cut to see what happens when you're doing constant surface speed. Okay, well the inertia is quite high and it does struggle to decelerate fast enough coming down, and that's mainly because those are CVT moves which move at a fixed speed. You can't change the rate of CVT bumping because it's a fixed speed 3-phase motor that does that adjustment. But all in all, it does seem to be pretty promising. I think it's probably time to chuck up a part and have a look and see what it looks like in action. Well, since I'm having difficulty getting my carbide to adhere to my trepanning tool, at least with the high silver content brazing silver solder that I'm using, I figured I'd go looking and found a couple of these professionally brazed tools and had at one of them with the tool and cutter grinder. Not sure if that neck's going to be strong enough, but let's give that a go. Right, I just went and blued up the spindle. Pretty happy with how that's touching. Seems to be nice even contact, so it's good. Now at this stage, I'm very close to kicking both this and this off my board because that program is mostly working quite well. So it's following program speeds very, very well. And that was my last major thing I need to do before saying that the actual Linux CNC conversion is complete. But I still want to tweak that a bit, so I'll leave it on the board for now. Okay, I've burnt up an insert, so I was obviously moving too fast there. So that was a surface speed of 200. Guess I'll take that down a bit. When I switch back to this screen from any other screen like Edit, it always scales to this size. Now you can see an outer red line there, which I assume is the maximum boundaries of my lathe, and I don't understand why that's reduced so badly in size. Every single time I have to scale it out like crazy. Now, if anyone knows how to reset the default scale value in Gmoccapy's preview window, please let me know. Whoa, roll back. What the hell happened there? I thought that whole spindle thing was going swimmingly well until I got to that commanded speed change where it's supposed to come out of back gear and then accelerate to quite a high front gear, and it seemed to have done that without a pause. And now something's making a thumping sound. Let me change gear. Ooh, yep, something is definitely bent, broken, or unhappy here. Ah, bugger.
Tomorrow for sure.
Alright, let's take a look at the belt. Okay, motor's running and nothing's coming out. That's not good. Have no drive coming out through the drive system. That looked kind of wobbly. Now I need to look around the back at that CVT, don't I? Okay, well, looking in here, the first obvious thing I can see is that the CVT belt is on the lowest ratio, like smallest diameter on the bottom, but it's not out at the largest ratio at the top. Looks like got a bit of bouncing around going on here. This belt is extremely tight. It's supposed to be. Let me switch gears. Something definitely unhappy on the output side of this thing. What does the input to that CFD look like at higher speeds? First glance, that's not good. This belt has ridden up over the edge of the toothed drive pulley. I'll have to release the tension on that. Yeah, let's crank up that whole motor unit. I wonder if that alone was the problem. Right, that all feels smoother. There were some comments on putting some form of optical encoder, like on output of the gearbox or on the continuously variable transmission. But really, this is a pretty dirty area. You know, you've got a lot of belt rubber coming off. It's all a bit oily because of the lubricated air that moves the gearbox. So I really don't think it's a great environment to try using an optical sensor. While I'm in here, I can do a quick oil check. It's looking fine. Let's just run that spindle and see if it's going to ride up. That's pretty scary when you have things like this happening, but I think it's just the belt riding up. I hope that was the only issue. Time will tell. Yeah, I think I will go into that software and work on the inhibits a bit and try and make sure I don't get that extremely fast switch around from maximum speed in lowest gear to maximum speed in highest gear. I'll have a look and see how I can inhibit that. Probably the best way will be to do it off spindle speed and make sure I have had a completely stationary spindle or near stationary spindle before the switch occurs, which I thought I already had, but obviously need to recheck that. Mail time. Can't remember what I ordered here. It's the wire I need for wiring up my control cabinet for my surface grinder. Oh, this is coming from Malta, from my mate Luke. Luke likes auctions, so he often picks up a bunch of quite unusual little bits and pieces. I'm guessing that this is some sort of a depth gauge. This is a fantastic little tool. This is for dressing an angle onto a surface grinder wheel. Perfect. I've been looking at getting one of those. Little sign plate. Brilliant. Luke's got the same surface grinder as me. His main belt drive was kind of worn out, and mine's got a few defects in it as well, so he made an order for both of us so that we could just save on postage. So this here is the main drive belt for the Jones & Shipman. This is my mate Franz's cam. It's for a flute grinding attachment, for grinding things with 3 flutes like this, putting the back relief on them. Luke has the same machine as Franz but didn't have the treble cam, so he borrowed my mate Franz's cam so that he can make his own version of it. I have to return that. What do we got here? Looks like inside micrometers. Got a similar set but only much smaller. These are the ones that you can use to sort of stack them together so that you can measure accurately much larger inside diameters. Whatever set I had only went up to like probably 2 inches or something. So thanks a lot, Luke, that's brilliant. Now this is coming from Martin in Berlin, and he's been talking about this because he's got the same lathe as me, and he had a better solution for getting the spindle control working. He used the feedback of motor speed from his VFD to calculate the gear ratio. I think his VFD outputs a signal in milliamps or so, whereas mine puts out a voltage signal and would need scaling. So he whipped up this little op amp, which he said should do a good job of scaling my output signal for my VFD. So I'm going to have to wire that up and give it a go. Well, thanks a lot for watching. Bit frustrated that I still don't have my set of surface grinder wheel hubs completed, but I'll get there.